Good. So last time we talked about flow control, and there is a few more things that we will need to take a look on before we are done with the basics. So for today we will take a look on pointers, structs, and if we have time, maybe we can take a look on functions. And once we are done with functions and then later memory management, that would mostly cover the very basics, and we can start writing some more useful code than just this proof of concepts implementations. So that didn't work as expected. It should go full screen. It kind of went full screen, but it didn't. Okay. Then let's not do it full screen. We'll keep it as is in this size. I will. Guess I need to reboot because for some reason it should actually hide the taskbar when I go full screen with the VM, but here in this case it somehow doesn't do it, so probably some Windows bug, and rebooting usually helps with that. So we create a new project, console application. Next we will call it pointers, and we will start with pointers. So as I already mentioned, I think during one of the last lectures, the idea of a pointer is basically to have a variable which holds a address of another variable, or more generally speaking, the address of a block of data, which can be a variable, can be multiple variables, etc. And then a pointer gives us the ability to do something with this address, to access the variable and stuff like that. So let's start with defining some variable. My var is equals 1, 2, 3. And now let's define a pointer on this int asterisk. My ptr is equals null, and let's define a few more. So we have an int. Let's go with also defining a short and a char that is big enough to fit in the char. So my var, let's call it my int, my short, and my char on my byte. And here we will do the same thing. We'll just go with my int ptr, and then we just copy this a few times. Zack. Int my byte. And now let's do some more thing. There is a nice keyword in C++ which allows you to retrieve the size of a variable. It's called size of. Oops, it's not typing. Focus is missing. Size of. And there you can specify a variable type, and what it gives you, it will return you the size. So const int size of my int is equals size of int. Then let's repeat that again 3 times. So for short and for byte, my size of my short, size of my byte. And if we define it anything as const, then the compiler will actually evaluate this. Sorry, not the compiler, the IDE will actually evaluate this in real time. So you don't need to compile the code, you can just move your mouse in Visual Studio over the variable, and the compiler tells you the value of the variable, not the compiler, the IDE. The editor tells you the size of the variable. So in this case we see that a byte is obviously 1 byte long, a short is 2 byte long, and a integer is 4 byte long. And now we can do the same thing, but this time for the pointers. ptr zack 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 zack, and we see now that that the pointer is here on the integer 8 bytes long, on the short it's 8 bytes long, and on the byte it is also 8 bytes long. And since this is a memory address, this is obviously reasonable, because the memory address space in a 64-bit process is always 64 bytes in size. So functionally a pointer will just be a underscore underscore int64 type. If we switch here the platform to 32-bit, then these variables, they keep their size since they are defined this way, and the pointers shrink to 4 byte, which is 32-bit. And of course here we only have 4 GB of address space available, so that makes sense. Let's switch back to 64-bit, and now let's see how we can assign a variable, a value to a pointer. And I think I already showed this slightly when we were giving the last homework assignment. So you've seen that you can get the address of a variable by using the AND operator. So here we try doing this systematically, and this way we can retrieve the address of where myInt lives in memory and assign this address to our myIntPTR variable. An interesting thing about pointers, since they always have the same type, is that you can also define a pointer that can more or less point to anything, but we will do this in a second. First we will see how we can assign a value to the variable where a pointer points to. We do this with the asterisk operator. So asterisk pointer equals, let's say, 456, will assign 456 not to the pointer but to the variable the pointer points at. And this is also why here, when defining a pointer, we always specify a type and then make it a pointer, because this allows us to use this asterisk operator since the compiler knows which type the variable should be. Of course, as we have seen with the casting of our float and double in the last homework assignment, in principle we can cast any type of pointer to any other type of pointer, but the compiler will of course just handle our object as the type of which the pointer is. The compiler will be unaware that we might have assigned a memory address to a pointer that does not contain a valid variable of a given type. So this already indicates that with pointers one has to be quite careful when using them, especially when using them in certain ways, because there is a great opportunity to make mistakes and corrupt some memory. There is a type of pointer, void asterisk, which can be anything. So if we now here go down and we have our integer pointer, let's go for our shared pointer and try to assign a pointer to another pointer. If we try to assign a pointer that points on type int asterisk, so that points on type int, to a pointer that points on type short, the compiler, or rather the editor, but the compiler as well, complains. So the editor complains that this is not a valid conversion, and if we try to compile the project, then the compiler will throw an error saying again that it cannot convert a pointer of type short to a pointer of type int. And we could of course force it with the trick that we have learned last time for the floats. If we just write short asterisk, then we kind of force the compiler to do it. Since the variables have the same type, it can just copy values from one to the other. On the hardware level, whether this stands here or not is meaningless. The only changes that if we don't have the right casting, then just the compiler will decline this operation. But if we have a pointer of type void, we can assign anything to a pointer of type void. It is basically the most let's say basic pointer you can have. It can be anything, so you can assign any type you want to a void pointer, and it will be just happy to accept it. When we take a look on a few things that you can do with pointers, it is important to keep in mind that some of those things don't work if you have void type pointers, because simply since the type information is missing and these operations are dependent on this information, the compiler doesn't know what to do, hence you need to then cast the pointer to something with a specified type, such that the compiler will know what to do. Pointers, as shown here, work this way in C and C++, work the same way in C and C++, but in C++ there is an additional method of using pointers, let's say covered or hidden method of using pointers, which is so-called references. So on a technical level, a reference and a pointer is the exact same thing. The difference, however, is that in C++, when you are using a reference, then the variable that you get as a result, you cannot treat as a pointer, you can just handle it as a normal variable. The pointery nature of that variable is, so to say, hidden away from you. So let's do that. Int, and here to make a reference we use the the reference operator, the address operator, the AND operator to get my ref, or no, let's call it my int ref. Let's call it my int ref, that, to be consistent for other naming scheme. And then we can just assign a variable. So as you see, you don't need to get the address from the variable, you just kind of assign the variable. But when we then take a look into how the code works on the machine side, we will see that more or less this line and this line should be kind of the same, just that simply because it is the same, but for us the compiler abstracts this pointer property away. And the most important difference here with these references is that you kind of cannot make a reference point to something else. So you must define what the reference points to when you create a reference, and the only other ways the only other things you can do is just whatever you do, like this ++ or this equals 456. It will always dereference the address and apply the changes to the variable you were pointing to. There is no syntax, no supported syntax to easily get the address of this thing out again. So it's basically a convenience feature. It's particularly useful when using functions. So when you have arguments for functions, it is helpful to specify those arguments as references, especially if you have more complex types, because then you can avoid unnecessary copy operations. But this we will take a look at when we take a look at functions. So let's keep this, and let's put a breakpoint somewhere, one here and one here and one there. Maybe better here and there. Yeah, we will inspect both, and let's run it. Zack. We forgot to remove all the to disable all the unnecessary code paths that are used, like this runtime checks and just my code support. So let's quickly do that. So general just my code support, no. Code generation, safety checks, no, and runtime checks, none. It should be, it's not all, but it should be good enough. So now you see it's already much less code that was generated. And here, as you see, the operation to assign here our address of my int to the pointer is just we load the address. So my int pointer will be stored in Rax, and then we no, wait, what do we do? That should be the address, load the address. So here we load the address, so my int, the address of my int will be stored in Rax, and then we just move the register content to the memory where my int pointer lives. And then if we try to assign something to it, again we load the address from the memory to the Rax register, and then we use another move operation to write to the memory at the position, at the address that is contained within the Rax register, and there write the 1ch value, which is hex representation of 456. And then if we continue our program and go to the next to the reference part, we see that it pretty much generated the exact same code, except of course here for using a different value. So as you see here, functionally both things, a pointer and a reference, behave exactly the same way, just that with references you don't have the risk of doing all the potentially dangerous things, at least within reason. So what you could of course do is you could take a reference myref2 and want to assign to it this, and what this basically does, it creates here a reference that is pointing at this pointer, and since this was created as a pointer, it might have been pointing to some memory which you could remove in the meantime, and then your reference will still then refer to some invalid memory address. So of course it's not completely fail-safe, but when you are using it as intended, the references are quite a nice mechanism to avoid all the pitfalls that are present when working with pointers. So the next thing that is related to pointers and is very important are arrays. So as you may imagine, you might often want to not just store like one value, but you want to store a whole array of values, a vector of some sorts, for example. And how would you do that, since unless we consider the vector extensions of CPUs, which usually we don't use directly, we just use libraries that use them. So how would we then represent a vector? And it is actually quite simple. A vector of variables of a given type, or an array of variables of a given type, will just be one large consecutive block of memory, where these variables will be just put one after the other. So let's define our first array, int my int array. We can specify a size, and then that would already be it. So we just write the type, then the name, and then in square brackets we specify how many elements the array should have. And what we can do, as you have seen already here, whenever defining a single variable, we can assign it a value, and in fact we can do the same thing with an array, just that we need to specify a lot of values. And in fact, if you are specifying values, then you might also specify your array like this. So not tell it how many elements there will be, because the compiler in this case just looks up how many elements have been assigned, and then it is fine with that. And of course, if you specify a size, you are free to assign less elements. What the compiler will usually do is it will pad the remaining array space with zeros. So you should get a defined state. What you cannot do, of course, is you cannot specify an element more than what you told the compiler the array will be large. I think my English is a bit broken right now. The grammatic of the sentence was terrible, but I think it's quite clear what I meant. So we cannot assign additional elements, and of course if we don't specify a size, then we can assign just as many as we want. There are some practical limitations regarding how many elements can really be assigned. This is more or less given by the limitation of the size of the stack. So you cannot exceed that size, so you would not create static arrays with, let's say, a megabyte or a couple megabytes. That would be unwise, and over a given size would not even work. So with a too big array, the compiler would even complain and not allow you to do it. How to then allocate arrays which can be gigabytes in size, we will see a bit later when we take a look on memory management, because there are ways how you can get memory other than taking it from the stack, and there you are not constrained almost at all with how big your memory block can be. Well, you are constrained basically just by the limits either of the address space or of your physical available memory. Okay, right. So such an array, now it obviously is good to know how one could access the variables, the members of the array. It's quite easy. Let's just take our my int and assign to it say the fourth value. And the way this works is that the first element is 0, has address 0, and then this one has address 1. So if we assign here the element 4, then we would actually be assigning the number 5 from our array. So actually maybe it would be better if I just define the array like this. Then we would be assigning the number 4. And here in the square brackets we are not restricted, of course, to use constant values. We can use other variables or write entire equations, and then the result of the equation will be taken as the address. So for example, if we want to have a loop which will do something with all the variables inside our array, so let's say we reset our myInt to 0, and then we make a for loop for int e is equals null, e is less than size of my array, but careful, so the name is wrong, my int r, but careful, the size of, as you see here, it gives you 40. It doesn't give you like 10 or the count, it gives you the size of one element times the count of elements. Hence we had to divide by size of my array, and we can just specify element 0. And then of course last thing is we want to increment our loop counter for the next go through, and with this loop we will access each entry in our array once, and we can, for example, accumulate all of them in our myInt variable, and that would be it. The simplest thing, the simplest way of doing something remotely useful with an array. Let's maybe put a breakpoint somewhere and run it so that we can see how this looks. Okay, so here we kind of don't really allocate any memory, because somewhere at the beginning of our function here we just reserve a large piece of the stack which is big enough to contain all our variables for the function here. In principle, we could grow and shrink the stack within one function on a as needed basis, but that would rather complicate things and would not really have any benefit to anything. So the approach of just allocating the maximum amount of stack space needed inside the function at the beginning is a perfectly valid approach, and there is no reason to not want to do that. So here what we do, the only thing we do is just we have our base pointer register RBP, to which we just in this instruction add different offset variables. We can show the code bytes maybe here. So we have some characters. Well, probably it is encoded inside. So presumably it will use 2 characters for the opcode itself, 2 characters for the offset, and then 1 character for the offset, sorry, and then the last 4 characters are the values which we assign here. So the way this works, we could assign any 32-bit value to any of our entries. So here, as you see, it increments in steps of 4, and that's how it works. So you can of course play with this opcode in this online assembler, disassembler, which I have shown you already. But as said, the understanding of how the opcodes really map to their binary representation, it's a fun thing to play with, but not something that usually is needed on an everyday basis. Show code bytes, right? Then of course here, when we want to take a value from the array, so it first loads the value into a register, then it multiplies the value by the size of one array cell, and then here it already then here it wants to load the resulting address, the final address, where it takes the base pointer plus the offset of the array plus where our array starts. So we see our array, the first element in our array is base pointer plus 50 hex, and here we take our base pointer 50x and our rex, which contains the offset in bytes inside the array, and with this value we can here finally move this value to our so move to this value our data. Here we just reset, and of course the loop we don't need to go through it since we know already how loops work. So let's just click continue, and then let's see how else we can access individual members in an array. So one important thing to know about arrays and pointers is that with regard to the syntax of the language, they are pretty much identical. They can be handled pretty much identically. So here we had a pointer to which we just assign something, and we can take our array in principle asterisk array and then assign to it, let's say 100. And if we run this code, then we will see that we have pretty much just assigned to the first entry in our array. As you see here, it's in, so 100 in hex is 64, so we have, as you see here, assigned just now to the array as if it would be a pointer, and it worked out fine. And this theme more or less continues throughout the whole pointer and array story, with very few limitations. They behave identically. One very important limitation is, for example, here this size of. So while you take a size of an array, it will give you the actual size of the array. If you take size of a pointer, it doesn't matter what the pointer points to, as we have seen already here. A pointer always gives you the size of a pointer. So the size of a pointer always gives you the size of a pointer, obviously, and not the size of an array. So a pointer is ultimately completely unaware of what it is pointing to. On the hardware level, it's entirely unaware. On the code level here, the compiler knows that the pointer was defined with a certain type, so it assumes this is what the pointer will always be pointing to, but there is no mechanism that would enforce this on a runtime level, at least not with normal compilers. You could of course use some sort of specialized compilers that might add additional bug check code, or also here actually with this compiler, this runtime checks when operating with some pointer types would also catch a group of potential mistakes. But these are like special things, and usually would not enable those in a release build anyways, because of performance reasons. So it's simply good to assume that the compiler will just do whatever you tell it to, and it will not try to fix your mistakes for you. So let's see what we then also can do with our array. So what we also can do is we can have like define an int asterisk my array pointer, or my int array pointer, let's call it my int array pointer, and then just we can assign the array to it, and this also works just fine, because as said, an array is kind of almost a pointer, and at this point the assignment works just fine. So let's now copy our loop. Oops, but let's try to access the content within our loop slightly differently. So instead of using this method, which we could, so if you have a pointer, or if you have any pointer, so for example even here, instead of asterisk something, we could always write 0 is equals, and it does the very same thing. But of course we don't want to do this, we already did it, so we want to do something else. So what we here, for example, can do, first of all, of course, we reset our counter again, just for good measure, and then we will plus equals, and what do we know? We already know that we can do this to get the first element. That is good, but not good enough. We want somehow to access then also the second and third and so on. So what we do is we just use pointer arithmetics, and this gives us access to the ith element of the array. And the way this works, if we look in the compiler, it is pretty much very similar to what is done here. It just takes the address, it adds I times however large the type is, and the resulting number is pretty much the address of the element, and then we just need to read the memory at this address. And a important thing to take into account here is that is that the compiler, in principle, what it does under the hood, we can write this down, int asterisk my temp int ptr, it just generates an intermediate pointer plus e times size of int. Of course, this at this level is kind of broken, because the plus operation, it will, whatever number stands here, it will actually take it and multiply it by whatever the size of our type is. So the code as written here would actually not work as expected. This is more for reference what the compiler does. And another thing to keep in mind is that such pointer arithmetic, so adding an element count to a pointer, does not work if the pointer is of type void. So if you have a void pointer, you cannot change what it is pointing to in this way. Usually if you want to do some byte-wise operations, so if you would want really to move your pointers by a certain number of bytes, which is not a multiple of the pointer of the size, you would just cast the pointer to a byte or char asterisk. And then, since then the size of one element is 1, you can just move and assign and do whatever you want at the finest granularity that is available to you. If you want to fix this code to actually work properly, you can make char asterisk like this. But this now, at this point, the compiler would complain here, because now the result is still of type char asterisk. So what you then need would be to cast back int asterisk the whole thing, and then only you end up with pretty much the same index that you would have. So what we can also write here as a comparison, we could use the reference, so int reference my temp int ref. Should probably add some array in the name, but it's clear enough anyways. And then we just take our array from I, and kind of this and this functional will be the very same thing, just that this one, the compiler, I forgot the semicolon, the compiler kind of constructs for us, while this one we have written by hand, and given and we needed two casting operations to just make the compiler do exactly what we want, which in C is quite a typical thing. So you can make your C program do arbitrarily low-level things, almost at least, but then you might need a lot of cast operations and other special operations. There is a certain subgroup of functionality which you cannot directly access with C, for which you would need to write some assembler code, but I think we will not be looking into that, as this is kind of a bit too complicated. So let's see how else we can play with pointers. We will reset our variable again. We will create a new loop but this time, instead of having a counter which advances and then we need to do multiplication and so on and so on, so everything is kind of not necessarily the most performant thing, we can be quite efficient with a small trick. So we can define int asterisk my ptr, let's go with this name, is equals my array. So this we already have shown that this works. So we can assign an array to a pointer, and then we need some condition. And what we can here is what we can do here is my ptr is less than my array, my int array, plus 10. So functionally, the number, we should take a look on this in the debugger. The number will effectively be like not plus 10 but plus 10 times size of int, so plus 40. And somewhere I dropped the semicolon. Right. And then of course semicolon, and then my ptr plus plus to advance it by, again, not by one but by one element. One element is 4 in size in this case, so it advances and increases the number by 4. And here finally we can assign our current number just by dereferencing the current value of my pointer. So the way this works is that the first element here has a certain address in memory. This address will be copied into my pointer, and here we calculate one address after one address after here the last element, and this way it will abort at the right moment. This might not be the most performant way, because it will here probably, it will depend how the compiler optimizes it. It will either write here just 40, or it will always have a multiplication, which would be not the greatest way, because as I said, multiplications are inefficient. But if you would see that your compiler is not doing a good thing, you could always just put this into another variable. Actually, we can my end is equals this, so this is then only this then only happens once, and then you use your variable here, right? And then I should also move this there, and then you are then you are sure that here it will just make a comparison and it will not need any additional calculations. And what we can do, since we have the same type, we can in fact move this into our can we? No, we can. That might not work. Why is it complaining? Asterisk needs to have an asterisk here. Right. So as I hinted at during the last lecture when we taken a look at flow control, there you can to a certain extent pack more than one instruction into your into any of those statements. The comma here allows you to, so you start with defining a variable, and then you can kind of define multiple variables in one go, and then you can also specify the assignments to these variables. And you could in principle here also use comma and then increment something, but of course in this case we don't want any additional incrementation. So let's quickly run, and then we will see how efficient the code was implemented when we go to the start here. Add 4. Let's see. So first it loads the address here. Let's see symbol names. It should help. Well, it doesn't help much, but it loads the address and it copies it here. Then it loads the address. Okay, so here actually in this one line it already did the whole thing. It just does this calculation, it knows the address, and then it uses just base pointer plus this. If our int array would be just a pointer, this would be a bit more complicated. We can force it to do this way. I'm just not sure whether, in principle it should have done the assignment, so then we should be able to do it like this. It is not complaining, so it should work. So here when we look now, thing is a bit more complicated. Again, we just load the address the same way, but now here we don't use a load address instruction, but instead we add 28. That is probably was the hex disable button. Nope. Hex return of hex, and then go on 20. That's our 40. So as you see, it did the necessary multiplication for us, the compiler, and then just entered the right value instantly, the right offset value instantly, so that it is quite efficient. Even if you would not use this end but have had this to be recomputed each time here, it would be quite fast. It would more or less just add one more operation. But this way, by using slightly more memory, we can make the code just that slightly a bit more efficient. Right, do we want to take a look at anything else? No, I think that's fine. Before we continue, are there any questions? Okay, ask away. Which line? this one there is no and. We have asterisk, we don't have an AND operator. We have just asterisks, which means that this variable and this variable are supposed to be pointers. You mean here? No, because it's an array, and an array can be handled like a pointer directly. Okay, any more questions? Okay, since there are no more questions, maybe before we continue with a bit more pointers, let's try to break something on purpose. So we have here our variable. Do we need this? Yeah. Okay. We don't change it anywhere, I think. Yeah. So let's define another variable here. Int my test bar equals null. And so basically, what we expect when the code runs correctly, when we are at the end here, this should contain the values that we assign to it. My int array, when we can take a look here in these locals. This is quite a useful thing, but it kind of, for arrays, it only works nice if the array is redefined with a size. If you would assign the array to something like we did here, then with my int array putter, there you see it only kind of gives you the first element, but it doesn't show you all the other elements, because at this point it just knows that's a pointer, and it kind of forgets that it was assigned from something that had 10 elements. So the count of elements for an array, as the array was defined, is not part of the array anymore. So the array doesn't know how big it is, only the compiler knows while it creates code, and it must create code that will kind of respect the constraints of the array, and it should do it at least, but in reality it really kind of doesn't. So maybe actually I didn't test it whether it is smart enough to do that. This is already invalid, but as we see, even though it was defined, it kind of at least didn't even throw us an error, but it throw at least a warning. So you see here, it told us that the array is 40 bytes in size, but we are trying to access it at offset 44, which is no longer valid, but it just fine compiled it. And if you would here, for example, don't take the size, but like just wrote, I don't know, 20, then we would just go past the array, and there would be nothing in the way the code is executed that would prevent us from doing so. So as you see, it's quite easy to access invalid memory, and maybe actually we should do it others. Instead of maybe test file, let's call it test array. We just make a test array with 3 elements, all of them 0. As mentioned, it pads the other elements usually with 0, so it should be fine. And what we do now is from int e is equals 0, e is less than 3, e plus plus. Oops, it should be a semicolon, not a double point. Then we access our test array at the index I and set it to -1, let's say. So at this level, of course, everything works because we used the right value. So we see our test array contains -1, all f's. Our int array contains still the values it should contain. But what we can do now is we can just tell it to go up to, I don't know, 30. So far past where it should be, where it should end. And did it crash? No, it hang. Actually, I would expect it to either just run or crash instantly, but not hang. This is odd. Oh no, I know why. We should try a value smaller than 30. 30 is too much. I will explain what happened. Maybe 20. Yeah, 20 is good. So as we will see now, of course, our test array was properly overwritten. I mean, there is nothing wrong with overwriting the first 3 elements, but then we kept overwriting memory past the end of the array, because as mentioned, the size of the array is not part of the representation of the array in memory. And the result is that my int array now also contains all f's. And when we had here 30, it overwrote so much memory that it overwrote also our I, and our I was always reset to -1, resulting in the loop just running forever, and actually never going past overwriting the I. So as you see, as soon as you start corrupting memory, the behavior of your application will be everything but what you have expected, probably, unless you kind of really well thought through your memory manipulation. So this here illustrates very directly, very concisely, why C++ is kind of considered a little bit dangerous, because there are no safeguards against such forms of memory corruption. And while just overwriting some data with garbage, you would think, okay, then the thing will crash at some point, or produce invalid output, but well, that might not be a bad thing. Might be annoying, but not a catastrophe. Of course, if your code runs a nuclear reactor, that's a different story. But in fact, such a thing is kind of very dangerous, because given that in the memory space of your application you have executable and code and date and memory containing data in the same address space, so on other more exotic architectures, on Harvard architecture type computers, this is not the case. There you have one memory for data, one memory for code. So there this problem doesn't exist, but in von Neumann architecture type computers, like the x86 architecture is, you have the same memory for both, meaning if you overwrite enough of memory, at some point eventually you will start overwriting memory which contains code that will be executed. And now simply what happens is that if you do that, you can overwrite the code of a harmless application with some malicious code that will start a backdoor, start some other code, and then start a backdoor, and then you have a big security issue. So such a sort of problems is at least was very popular in the last in the 2010s and so on. Only I think with XP Service Pack 2, yeah, I think it was Service Pack 2, there started to be safeguards implemented against such attacks, and they were based on pretty much just adding a new feature to CPUs that allows certain regions of memory to be marked as not executable. So ideally, when you have program code, you would want to put it in memory which is executable, but not writable. And if you have data code, well, not code, just data, then you would put it into a memory which is readable and writable, but not executable. And this is something that was introduced only with a update to the CPU specifications. Very old systems don't have such features, and the granularity with which you can set those properties for your memory is about the page size, which is about 4 kilobyte. So for every 4 kilobyte block in memory, you can define whether it's readable, writable, executable, or none of those things. And the only entity inside your operating system that can change those flags is the operating system kernel itself. So when a user mode application cannot change those parameters on a hardware level. But what it can do, of course, it can request the kernel to do a change on its behalf, and then of course it's the kernel's responsibility to first validate whether it is safe to do so. And at this point, one of course could say, okay, so if code, if you have pages with code, even if you would not have the ability to mark them as non-executable, as long as you can just mark them as read-only, then shouldn't that be already good enough to be safe against such overwriting attacks? And if your goal when overwriting just memory would be really to overwrite just executable code, then such an approach would already work. But given that the code can live more or less anywhere inside your memory space. What also can happen is that if you overwrite other parts of the data blocks, for example some return addresses or function pointers, then you could still get the CPU to try executing code which is in a data block, which, well, is a data block and should not be executable. That is why they needed to implement this hardware, this special hardware feature. And on a tangent to this, so with this non-execution bit, already in one go a huge class of security vulnerabilities have been remedied, at least mostly. It is usually with such changes not as easy that you just enable it on the operating system level and then every application becomes secure, simply because applications may on purpose define memory areas where they want to change their own code and do any sort of weird things. So normally an application should in its manifest must specify whether it actually supports the non-execution bit or not. Normally any modern application that you compile by default will be set to support all those things. So this is not something that one needs to take care on consciously. But what then hackers invented to still be able to redirect the execution of code is, well, again, they want to override something using such a exploit as we shown here, but now their goal is not longer to override executable code, but override the stack of the thread they are running in with a list of return addresses. This is a bit now already going ahead to how function works, but since we had this topic, let's just quickly finish it. When you have a function and you enter a function, you can enter a function from anywhere in the code, and then what you want to do once you are done with executing the function, you want to return the control back to wherever the function was called from. And this is simply done by, when you call a function, the call opcode puts the return address on the stack, and then the function is executed, and when you then invoke the return opcode, then the address is taken from the stack, and then it jumps back to wherever the function was called from. Now if an attacker manages to overwrite the stack of a function, then they can specify an own address where to return to. And this doesn't sound very useful, but it actually is, because what you can then do is, if you know the application which you are attacking on a binary level, you can find functions which do some very small portion of computing at their very end. So obviously any function, whether it's big or small, at the very end will just have a few more instructions and then it's done, and then it has the return code, and you can just string together an arbitrary, or not arbitrary, but a very long chain of such addresses of function ends, which each will do something and then return to something and then return, and then instead of returning to where it was called from, it would return to the address of that is specified in the stack by the attacker. So this way you can get kind of code execution. It's called return-oriented programming, and you can make the CPU still more or less do whatever you want. It is much more convoluted, but still you can manipulate the registers, and with automated means of finding such suitable jump targets, this is not even very difficult. Like, it's not labor intensive. You need to have the know-how, but it's not a laborious process. And with I think Intel 11th gen CPUs, maybe or maybe 12, I don't remember exactly. With AMD, that was I think Ryzen 3000 and newer, have introduced again a hardware mitigation against this sort of attacks, which is called shadow stack. The idea there is that when you invoke the return instruction, while it of course takes the value from the stack and tries to jump to there, the CPU on the hardware level will maintain a list of valid return addresses, and as soon as a return address is encountered which hasn't been put on the stack by a call instruction but by any other means, like an attacker overwriting random memory, then the CPU, instead of following this return address, will just throw an exception, and this operating system can terminate the application. So with this other change to quite modern CPUs, as you see, even the Ryzen 1 and 2000 don't have this functionality. So a very modern CPU will not, a system with a very modern CPU will not be that much subject to an attacker that is exploiting such a code weakness. But there are billions of computers probably around the world still in use which are vulnerable at least to such return-oriented programming-based attacks. So it is very important when writing own code to avoid any sort of memory corruption, not just to avoid your own application crashing or behaving erratically, but also to ensure that whomever is using your application, as long as they are using the application with data which are not generated by them but can be somehow given to them, downloaded from somewhere, etc., that your application does not become a security threat to your users. So it is, in principle, to summarize this, a good practice to try whenever possible not to directly access pointers and arrays, but instead use more complex data structures which are implemented in the standard template library, on which we will take a look much later during the course of this course. And of course, then it's obvious that since they are C++ based, those are only available in C++. So normal C cannot really be made safe. Hence, ideally, you should only use C++ for new projects. There are some edge cases where you might need to just write pure C code, but as said, you should avoid it whenever possible. Instead, use the modern methods. So that said, let's continue here with our arrays. So we will disable this intentional memory corruption that we had here. Oh, and of course, what you also see and learn is that the things in memory, they just really, more or less in the order in which you put them into a function, they will just exist one after the other after the other. There is no barrier between them. There is no nothing. It's just one large piece of memory with which you are really operating. Okay, so we had void pointers already at the beginning here. So let's quickly is there actually anything about pointers? We already right. There's one more thing that we can do. So you have seen already casting of types, which we needed for the homework, but we probably should take a look in this again in a bit more detail. So we'll move our void pointer further down so that we then can play with it. We have our void pointer. As mentioned, you can assign anything to a void pointer, whatever you want. But of course, now if you want to get the value out of such a void pointer, let's again assign my int ptr to it. Then you cannot use let's say int test is equals. You cannot use the asterisk operator because the pointer doesn't have a type, so the compiler doesn't know what to do with it. For it, it is just a number that represents the address. And as said, the way to get it out is that you use the cast operator. So first you cast the void pointer on a int pointer, and then you can dereference the int pointer and get the value out which you are interested in. Or you could use the same method to assign a new value to whatever your pointer is pointing at. And what we also have seen already are these const variables. The important thing here is that while this is kind of here shown as a variable, the compiler can choose to not use the variable but just use the value of the variable instead. So for example, we can demonstrate it here. First we try int my len is equals 3, and when we try to use this here, it will not work. And the reason is because this is a variable which could vary, obviously, and an array as defined here, an array as defined on the stack, must have a fixed size, always the same size. It cannot change its size during runtime. So what you can do is you can just define this const, and in this case, when we would take a look here, we would see that the code, whether it's len array or free, the machine code will always be the same. So it will, even though it might allocate memory for this variable, for this constant variable, and put the right value in it, just for debug purposes at least, whenever it cannot use a variable but needs a constant value, it will just take the value it knows the variable should have and keep. But what we can do with casting is we can cast, first of all we can, well actually we cannot, this complains because it's not type const, so you could have const void, or let's call it say void pointer, const void asterisk void ptr, so we can have a right, and we're also missing a reference. So okay, again, to demonstrate it, this should complain here, as it does that it cannot assign something non-const to, no, sorry, something const to a non-const pointer. The other way around works. Something non-const to a const pointer you can assign. So you need a const void pointer to make this assignment. But what you of course can also do is you can cast this to just a void pointer. You could also do it in one step. You could just have done it like this, but let's keep it this way. And then you have a pointer which kind of would be changeable. So for example, you could make int asterisk void pointer asterisk is like, let's say not what was it, says 3, let's make it 30 to break it. But the thing is that this, while it will change the memory where a copy of this number lives, it will not influence this array. So we could actually exploit this for our example. We just need to check how the compiler would handle this in practice. So it might be that the compiler will here also just insert the number 3 and don't care for what it is in the variable, but it also might be that it will actually use this variable, in which case we could introduce the error that we had before. So okay, we go 1, we go 2, we go 3. Yeah, so it actually we didn't trigger the mistake, because even though we have assigned, you see here, the value 30 to the variable, here in the machine code it is always comparing against the number 3, because it just remembered that's const, that was 3, it will always be 3. There is no point in taking the value from memory. Of course at this point we could write this, and then it will run here more than 3 times, and we will run into the query. You can also see here that the CMP instruction now is not comparing against a constant number, but is comparing against the value from memory. So it is a very good practice to not try to change const type variables by casting them on something non-const, unless you know for sure that what you are changing is not a variable which was used somewhere else, let's say. Right. So we have here our deconsting of consting. So to just finally summarize, the fastest way to achieve this is just asterisk int asterisk 30. So yeah, that can be easily done. And let's try one more example here. Let's have int e test is equals null x1 2 3 4 5 6 7 8. So we just fill in a integer, and now we have a char ctest, which is a array with 4 characters. So those two variables have the same size. Now what we can do is we can asterisk comma int asterisk comma ctest comma 2 is equals itest. So just for good measure we initialize this with zeros, null. And right, we need something to break at, so let's say return 0. Actually, we can just drop the brackets, then we don't need something to break at. And what we'll now see is that when we run this code, we will right, I need to disable our bug. Oops, that, the autocomplete interfered. Right, so now what we see is that we can in this way copy the content of our integer array to our of our single integer variable to our character array, and our character array contains, when we enable hex again, obviously individual values. And as already mentioned the last time, the order in which the bytes are stored in memory is kind of inverted. It's the little endian order, and the least significant byte is stored first, and then it's the second least significant, and the most significant is last. And here, when we take also a look into the machine code, we see that the way this copy is done, it would look the same way if we would be just assigning two integers to each other. So this really shows that what we kind of on a higher level of abstraction see and understand as integers, floats, arrays of things, on the machine level it's all just one big blob of memory, and the thing can do with it whatever it wants. So this much to pointers, and I think at this point we could assign some new homework. So what's today? 21 03 2024. Right, so here let's say this results in 0x87, 0x56, 0x34, 0x12, 1 2 3 4 5 6 7 8, right? And this is and pretty much any modern CPU uses the little endian encoding. Even ARM, which is quite flexible, uses little endian. On some versions of ARM, you can, in principle, during the early stage of initialization, actually switch the CPU to use big endian encoding. But this is kind of not done, and there really isn't a good reason to do so. So alternatively, we could have big endian, which is 0x12, 0x34, 0x56, 0x78. Right, and this would be big endian used, for example, in network protocols. And the homework assignment will be to write a coder block which can convert a int 32-bit int endian to it's to the one and vice versa. So I think this will be kind of easy, because you just need to, you could, for example, here, once you have this individual characters, you could just reshuffle them and use some assignment and a temporary variable to do so. Or you could use another whole piece of memory and just assign them all together. So it's quite easy. And then we'll add a part B. So 1 and 2. Write a code block which can add a 64-bit to comma, And here we make it a bit more fancy because we ask you to use a loop. So here for the part 1 you could really just by hand assign things around and that would be it. But here we add the requirement that you need to use a loop for it, and of course, and vice versa. So we want a conversion to and from big endian in both directions. Okay, are there any questions at this point? Okay, so if there are no questions, then I think we are done with pointers and casting in general. So let's continue to the next natural thing, which will be structures. So we create again a new project, create an empty project, console, structures. Okay, so as we have seen in the previous project, all the things, all the variables here in memory just live in one memory block, and one can override them mutually, so to say, if one exceeds constraints. So in principle, if we have, for example, a pointer to this thing and we know that this is free, we could retrieve the pointer to that thing just by doing some pointer arithmetics. But of course this would not be really nice. So what we will, for various reasons, one is of course that we don't know if the compiler will not reorder things, and second, there might be some memory alignment. So if this would be like 3 1 character large entries in the array here, it is likely that the compiler would kind of add a 4th empty unused byte just to have everything nicely aligned to improve performance, since when retrieving data from memory there are benefits to having a 32-bit or 64-bit alignment, as then the cache of the CPU can be used more efficiently and less operations on the backend are needed. So instead, of course, of messing around with pointers and so on, what we would want to do is we would want to make the CPU, the compiler for generate for us code that would allow us to bunch together a couple variables and then reliably access them. So this is what a structure is usually used for. So let's define our first structure, struct. So we start with the struct keyword, then we provide a name. Let's call it my struct, and then of course brackets. And then inside this structure, we can then define variables. So let's say int var a, and then we can add another one, int64 var b, and we could probably add some char var c and short var d, and another char var e. Okay, so we have created here our structure. We added a few members to it. So let's use it. My struct is equals. So first of all, this you can use a structure as any type. So instead of writing int name, you can just write the name of your structure and then a name. And you can in fact initialize the individual members of the structure. 5. This using the same syntax as you would for an array, just that here the compiler knows that these elements don't have the same size, and you can of course make the structure almost as big as you want with the same constraints as for an array. So you should not exceed like megabytes and megabytes of data. So you can of course also have an array here, int var f. That would also work, but it's not needed for this example. So let's keep it simple. And now let's see how big this thing is. So const my struct len is equals these off, and size and set. You can use either the name of your variable or you can use the structure type, so both will evaluate to the same value. In this case we see it's 24, but 24, is that correct? 24 sounds a bit much. Let's count. So this one has 4 bytes, this one has 8 bytes, this one has 1 byte, this one has 2 bytes, this one has 1 byte. So this should have 4 and 8 is 12, and 1 is 13, 14, 15, 16. So it should be, if I didn't miscount it, 16 bytes long, but for some reason it is not. And the reason why it is not, so why we here actually get 24, so we can notice that 24 is kind of 16 plus 8. So we have somewhere, oops, it should be a, so somewhere here 4 bytes are hidden which we have not allocated. And I already hinted at this. What happens here is the compiler tries to memory align those variables. So it wants, when accessing those variables, to be able to access them at a nice even offset. So what it does here, if we have 64-bit variables, so this will be the biggest size to which it will try to align everything. So here it will add an empty unused 4 bytes, and since everything in the end should be a multiple of 64 to have optimal alignment, it will add here another 4 bytes, even though they are at the very end and are not needed or used or anything. And then we will end up with 24 as the total size. So to illustrate this maybe even a bit more, so let's start with 0. How many space I need? Probably like 2 or 3. 3. Zack. Wait, I don't need so much. I just need to go to 7. Okay, so from here till 3-ish. Here we have our var A. And from here I probably should reduce this by 1, that then it will look nicer. Let's see, will it look nicer? Yeah. Right. From here we have just empty. Then we will have our var B. And then we will have C, D, yeah, wait, D is too long, E, yeah, and then we'll have an empty entry again. So this is how this structure internally really looks like, and you can specify through pragma commands a different packing order, so you could force the structure to not be not contain this padding fields, but usually it gives you at least noticeable better performance if you do it this way. So we will not be disabling it just now, and instead we'll keep looking what else we can do with our structure. So for example, one thing you could do is, if you want to save on this wasted space, you could just reorganize your structure. So we just copy it, and since we know that we have here 4 empty bytes, we can just take those 4, put them here, and then everything will be nice in memory aligned, and the structure will be only 16 bytes long. Of course, we need to give it a new name. Let's say mystruct2. So let's try it. mystruct2 then mystruct2, and what? It's still not. Let's one int char should be aligned, but it is not. Why is it not working? I think it does not like this. Yes? Yes. It is automatic. So when you have like something that needs a 32-bit alignment, and then you have a variable that would benefit from a 64-bit alignment, then it would add here a padding space on its own. And if you change the order, then you can force in the end the compiler to not add any padding, because you start with 4. So let's write this down again. So in this case we had variable so we have reordered our structure to be much tighter packed, and now the content looks like it's like here. And if I remember correctly, there is a command you can tell the compiler to not do this. What was that? Hash pack1, I think. Right. So if you can specify like a well packing size. You would not usually use oops. So first you want to save kind of the configuration of your compiler so that it doesn't affect later code. Then you say pragma pack1. This means you want the array to be just packed to a granularity of 1 byte. And then here, when you look on it here, there are no more empty spaces. So you have kind of disabled this behavior, and then this size is already, those have been eliminated. So you can force this, just that the performance when working with this structure will not be as good. So if you want to have good performance and use less memory, then you would need to change the order of your members manually, as we have done here. In this case, it is always 16, not 24, even though it contains the same amount of data. We just not need these empty spaces to have the right alignment from the get-go. Yes. You're welcome. Okay, so we did that, and then let's see how we can access something in such a structure. So let's go with int var a. We can reuse the names. So if there are names in a structure, we can use them outside that. It's just fine. And then to access something in a structure, we write the name of the structure, then we write dot, and then the compiler, the editor already then suggests us what we can do. So since we called our variable a, let's probably suggest we want to read the a value from it. And of course we could do then the same thing with b. I mean, this can be any name, maybe my var b, just to let's give them slightly different names to make it clear that this can be anything. And of course, when you want to assign, and first of all, this you can do for all the other members as well. And secondly, if you want to assign something to let's say I don't see, you can do it like this. So instead just of using a variable name, you would use just structure name variable name. And in fact, you could have a structure that contains structures which contain structures. So you could have like something dot something else, something yet again something else. So there is quite a potential of cascading and making very much nested objects. And of course, what else we can do? We can assign structures. So let's say we had here mystruct. We reduced mystruct to len, so mystruct, yeah, we still call it mystruct2 is equals mystruct. And when we now take a look into the generated code, we see that it actually needs quite a few operations to do this assignment, because as we mentioned already when we introduced variables, that the CPU on a hardware level can only handle machine types, and a structure is not a machine type. A structure can be a collection of machine types, but ultimately it is just a large piece of memory. So the way such an assignment works is basically it will try to copy the entire memory block, and here we see how this is implemented. So first we load the address of our target structure 2, then we load the into one register, the rex register, then we load the address of our source into the source structure into the RCX register. Then here we move those two registers into the RDI and RSI registers. I'm not sure why the compiler did it this way. I think it could directly load them here. The intermediate step is, I think, not necessary, but well, it did it, so okay. And then in the ECX register it loads the size, so the count of operations that it will want to perform. In this case 18 hex, which is probably 24. Where's the hex? Is the hex disable button? Disable hex. It is 24. Yep. And then what it do? It has this rep move s. So instead, so a normal assignment, like for example here, is just a move, but you can also use this rep specifier. Modifier rather, to execute multiple move operations. And the way this works is that you have rep, then you have the actual opcode which you want to execute. In this case you want to copy in increment of single bytes, which is kind of inefficient. The compiler could have here chosen to use double word or something bigger, so 32-bit in one go, then it would have needed less iterations, but apparently in the debug build it chose to do it one byte at a time. And internally the CPU, so you don't kind of need to write your own loop to copy. The CPU internally just will repeat this move instruction using the RDI and RSI registers as many times as big a number is in the ECX register, and each time it has executed the operation it will decrease ECX and it will advance RDI and RSI to the next element. So we can actually even see it. So if we kind of single step, we always step forward, but when we single step here we kind of are single stepping in place. But when we go to look at the registers, we see that the three registers as described are changing. So RCX is getting less and less and less, and RDI and RSI are getting increased by 1. And once we are done, so once RCX reaches 0, we then finally can single step out of our rep moves opcode here. And this is reasonably efficient, so assigning structures is fine. It works quite well. I'm surprised that they didn't implement it in a more efficient way, but in the debug build it is not expected to use the most efficient implementation, just rather ones which are very basic and can be neatly debugged. But of course what you also can do with structures is you can have a pointer to a structure. So if you would be calling a function, let's call this copy, then you could just pass a pointer to your structure to it, and then the function internally could just use your structure, and if the function is not supposed to modify it, then that would be just fine. Then you can skip the need to make an explicit copy, which always is a small or even sometimes big improvement. And now, since we have here our pointer to a structure, the question is how would we access a individual member? So one of course thing is we can asterisk and then dot, but that's actually not the way that is recommended to be used. There is a special arrow operator which can be used on a pointer type to access a member of whatever the pointer is pointing to. So here instead, if you want to reassign var a, but this time from a pointer, then we just use the arrow operator, which as said is equivalent to asterisk. No, the asterisk inside. Punkt. I mean, we can also just take a look on this, that those two things should be equivalent. So let's put a breakpoint there, let's run it. And when we see it is even though it's written completely, well, maybe not completely different, but significantly different, the resulting code is exactly the same. And this arrow operator is actually quite useful. We will see that later when we will maybe try to create a smart pointer. So this what a smart pointer is, we will learn later. But now we are still at the level of the basics. So as said, we can do this alternatively, or maybe let's just leave it here. Actually, let's just copy it, give it an own line, since it's nice to have. Zack, zack. Okay. Right. So so much to this. Another thing that probably is worth mentioning is that you can with any type, actually not just with structs, but with any type, you can have a pointer, and you can also have a pointer on a pointer. And in principle, you could just keep adding asterisks. At some point, it's just useless, but the general idea of having a pointer on a pointer is sometimes quite useful, because if you want to return an address from a function, if you want to return more than one address from a function, you could, for example, pass to the function a pointer to a pointer, and then the function could update the pointer with some other value, and then you could get this way your return value. So if we have, of course, such a double pointer, so let's call this struct pointer 2, then we need to assign this, and the simplest way to assign this is, of course, to either take an address of an existing pointer, or we could alternatively, of course, kind of take an address of the original variable. Well, no, that's pretty much the only way we can do it, because we kind of need a memory address which we can access. Why is this complaining? The asterisk is missing. Right, so we can have a pointer on a pointer, and then, of course, if we want to retrieve a value from that, let's copy this again. That complicates things, because we kind of that was pointer 2, so we cannot use the arrow operator on a pointer, because it kind of, the arrow operator gives you access to whatever the pointer points at, assuming that whatever it points to has members. But a pointer, as a simple pointer, does not have own members, so this doesn't help us. So here we in fact now need to use the asterisk. There is no way around it. And of course, in the other case, we can just add more asterisks. Oops. In this order, zack, to access, to dereference the pointer on a pointer. And that's that. As already, now, the next nice thing about structures is that, as already mentioned, a structure can not just contain machine types, but it can contain another structure. So let's create here a struct my struct x, and let's give it my struct. Let's go with my struct 2, because that one is more compact, as the x, some name, and then we can add to it in 64 a var f. So we just add another variable. Okay, now if we want to see how this will look in memory, we can just grab here our first one, since this one already was nicely aligned, and here b. So we see instantly that such a structure is functionally equivalent to let's call it my structure x, to just having taken the content and copied it here, and it's again the exact same thing. So we can here first of all let's check this. Let's use it. String 1, zack. Var S3b, let's call it. But we cannot assign anything to it. We can see how large it is. When is equals size of var b. I think that should be 24. Yep, since this one was 16, so when we add 8, it gives us 24. We can then do the same thing here. Just giving a different name. Let's maestro x, zack. And again, as you see, it's the same size. And of course, what we also want to is to access the members. So as said earlier, you can cascade as many A, B, C, D, E, F. That's not too much. Right, this one doesn't exist, and this one is one earlier. So as mentioned, if you have a structure with a structure with a structure, it would have like a lot of names and dots, and if that would be a pointer, then at some point you would also need to have a arrow at the right place. So if we would here take a pointer on that, my ptr is equals reference on this, then that would look like this. Zack. Right, so first of all we need to add pointer, then it should of course be complaining that it cannot work, and then we need to change this here to the arrow. Okay, and of course here it would be similar. So what we now can do, since we know that these two structures, this one and this one, in memory, I will shorten this. No, I will not. In memory look the same. They are aligned the same way. They contain the same fields at the same offsets. So what we can do here now is we can define a struct of this type as 4. The size we already had, and now we can assign to it. We want what we want to do. First, what we want to get this one and assign it to that one. And of course, the compiler says this is not allowed because it's a different type. Sorry, I cannot do. So what we do now is we get the reference on the thing, then we cast this to this, and then we dereference it again. Sorry, that's just the wrong spot. And now automatically it can do the assignment. And now if we try to read a value in 64, my test var f, oops, 64, zack, var f, it should give us the right value, zack, and it did. And also when we look here, it uses the same move mechanism as we have seen already before somewhere. What was that? Where did we have the assignment? Did I remove the code again? No, I did not. Var variables. I think I might have removed the code. Here. No, it should be somewhere there. Let's put a breakpoint here, then we'll find it. Right, so here, as mentioned, we have this, it kind of, even though in the later case we have a completely different structure, it uses, there's the exact same method to move the data. The only difference is that now 18H should be, actually that will still be 24, because before we demonstrated it with the other one, with the other structure which was differently aligned. So as you can see, there really is nothing in the hardware that would be aware of anything that is more complex than just a basic type. So here it really is the compiler's task, its job to safeguard against unsafe operations. But whenever the programmer, the developer, the code author thinks that they know what they are doing, it is possible to coerce the compiler to do anything we want it to do, even if in any normal scenario this probably would be unsafe, because you would not expect two different structures to be guaranteed to always have the same memory alignment and memory layout. So usually if you would want to kind of make a bigger structure containing another structure, you would just use this method here to just put a structure which is already somewhere defined, and then if you have the definition, then the compiler ensures that it will always here look the right way. And of course now if you were to change, for example, struct2 by adding a field or by changing the sorting order, a cast, right, not the cast, this cast here, if we don't adapt the struct x, would then start misbehaving and causing troubles, simply because it would not be aware that the structure changed. So it is really good to try to design one's own code in a way that makes it not just fail-safe but also safe against later modification. So you would try to design things such that if you change something somewhere, you would not need to propagate the change through the rest of your source code, but the change should be propagated by your compiler. An example of such a thing, actually we can take a look on here in pointers, pointers, here somewhere where the loops, here the loops. Here we already did this implicitly because we take the size of the array. One thing that someone that writes code would probably intuitively do is writing, okay, my array is 10, then let's just 10. This is fine, it will be fine, it will work forever until someone does this. Or, okay, 12 is not so bad, this is worse. And then the code fails. So you should really try not to write your code in a way that if anything about it gets changed would then result in a silent failure. So if you if you change the name of the variable, then this is not a silent error, because then everything further down says, okay, the old variable does not exist. What's wrong here? Fix it, please. But changes like here, they are not caught. You can change this to whatever you want, and the compiler will not tell you here that something is wrong. Maybe, like, if it's a really new IDE, then maybe if you try to compile it, it will actually be smart enough. Let's try something is right. First of all, we correct this. So that's an error that needs to be fixed, but here it does not complain even. It might throw a warning, but it did not even do that. So it was not smart enough to actually realize that now something bad is going to happen. I think if you would do it like statically, we have tested this before. Here, if we would try to access 8, I think it would at least complain about uninitialized memory, but no, it did not. It did not even complain in this case. So as you see, it is very easy to write code which will not be safe against later modifications. So you should always either try to use such a trick, or to define a const variable and then use this const variable in your loop instead, or something like that, so that you can be reasonably sure that when you later, 10 years from now, once you don't remember the details about your code, when you change anything to it, that it will remain functional, and most important, will remain safe. Okay, so let's quickly actually resave this and go back to our structures. And well, we are only half done with the structures. There is quite a whole another aspect to structures that we have to take a look at still. So these structures that we used here, as you have noticed, if you define members, then each member gets its own memory location. There are certain rules how this memory is aligned. It just more or less is exactly the same order that you provided, just with added padding, unless you specify this packing pack 1. If you would use like pack 2, then it would well, pack it differently. Then it would align to 2-byte boundary. Pack 4 is somewhat which might be useful if you, for example, would have some structures that need to be interoperable between a 32-bit and a 64-bit system. Then you would use a pack 4 and so on. But the other type of structure, which well, is not called a structure, is called a union. And a union is you can write it in a way which more or less looks like a structure, but it behaves differently. So if we in a union specify, let's say int var1 comma int var2 int 64 var3, all these variables will share the same memory. So if we use the union, my union, and assign var1 is equals 1, and then we try, and let's say then we try to int my test is equals, we can read var2, and it will read back to us the one that we have put into var1, because they have the same size and occupy the same memory. So voila, it is 1. And if we look on our union, we see that everything is kind of 1 except the top part of the int, because it was never assigned anything. So it is just filled with a value that is pre-filled by the code. Actually, we can disable this, I think, if we turn off all the this and that. Then it should, I think, be just filled with zeros. On very old systems, that actually would be just pre-filled with whatever was in memory before it. But since such an approach, obviously, so now, okay, now we have it's pre-initialized to a different value, but it did not actually clear it. What I want to say is, on old systems, memory was not really cleared unless the program decided to clear it explicitly. So the way this worked was that if you created a new instance of some application and just allocated some memory, then whatever you might get there would be just garbage from whatever other program used that memory before. And since this obviously is a risk of leaking data, more modern versions of Windows always clear the memory that is allocated to newly running processes. So technically you don't need to pre-clear it, but obviously it is recommended to always create a defined state. So if we want, in our case here, have a perfectly defined state, we just assign 1 to our number 3 variable, and as we can then see here, then all the variables contain just 1. And you might wonder, okay, what is this even useful for? Because if we do it this way, we have 3 names for the same thing, and some of the names are not even able to hold the whole data. So 0x, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A, B, C, D, E, F. So we fill in a full 64-bit number, and then we will see that the smaller ones, var1 and var2, will only hold a portion of it. So as you see here, they only hold the end of it, so the top is not even accessible. And there are a few useful, very useful use cases where this mechanism can be exploited. One, of course, would be if you have different, like want to have one large data structure, which would contain a variable which would define what the rest of the structure will be, and then you would have different unions. Well, sorry, one union containing again different structures, and based on the one or some parameters outside of the union, you would determine which of the structs inside the union are actually valid and which others are not. This is, for example, used a lot in the Windows kernel for various things. And if you want to be super memory efficient, this is a quite reasonable approach to implement objects which can be somewhat polymorphic in nature. So this means objects that can represent different things depending on other fields which has been already set in that object. That's one use case. Another use case is you can use these unions to quite easily manipulate data. So here, if we would put this 2 into a struct, so the struct, as we know, makes them live in different memory regions. So this thing is one entity in our union. This one is the other, and we can also, by the way, after defining a union or a struct, so first of all we can create a struct without a name, and secondly we can provide here a name, let's say u, if we want to. So if we have this u here, then we access by u1, and if we don't have this u here, then we can access it directly at the top level. Usually, to avoid confusion, it is good to have a helper name here, such that we know which variables are using the memory space of other variables and which are not. And what we now have done here is a very simple way to split a 64-bit variable into its low and high portion. So this is the low portion, and this one will be the high part. So now when we run it, we will see that now our union is already useful, because when we take a look on the union, our variable contains the whole 64-bit number, while our struct inside the union contains the lower and upper 32-bit of our 64-bit number. And when you have systems which handle only 42-bit numbers, it is quite convenient to be able to easily split larger numbers into the high and low portion. So this is one quite useful example. Of course, we can create a more complex union as well. So let's do that. Zack. Union, my union 2. Oops, it should be a small n. And so char bytes. Okay, so a 64-bit number has 8 bytes, so that's one thing we want to access. Then struct. Let's use shorts. Value low low, value low high, value high low, and value high high. So this way we can access the 4 shorts that make up our 64-bit number. Then we can of course do the same thing with int value low, value high. Right, we need names. Part 16, part 32, and then of course the value which contains the value. So you can make it as arbitrarily complicated as you want. Again, the size of the union, oh, we didn't do the size of, we should do the size of my union. So const int union len is equals size of my union. We don't need these brackets, so we see here it is 8 characters, and of course here it would still be 8 characters. So I think this is already obvious, and ultimately there is one more thing which one can do with structs and unions that is worth mentioning probably here, which is to create something well truly complicated. There is a syntax in C and C++ how you can in fact address individual bits or bits or nibbles or in principle any sub part of any bigger number in an easy way. So you do it by writing first of all you unsigned int your basic type, and then which will in this case have 32 bit, and then instead of writing a number, so normally for a variable you just write my var and be done, but instead what you do is you write say byte 1 doppelpunkt 8 strichpunkt comma, and this way you are telling the thing that here you want this to be 8 byte, and what you can do then is you can specify more of those. So let's say byte 2 will be also 8 byte. Why is it complaining? It should be not complaining. We need to put it in a struct. Oops, I need to put it in a struct first. Right, so now it works. Right, so we start with a struct, we start like this, and then we specify the amount of bits that we want every variable to have. So then we could, for example, go for nibble 5, which will be 4 bytes in size, nibble 6, which will be again 4 bytes in size. Then let's go with nibble 7. I will make a space every 8 bit. Nibble 7, right, and then bit 29, 1, comma 2, 3, 4. The last one is to be semicolon, so 29, 30, 31, and 32. Assuming we want to name them this way, we could also start indexing them with 0, but we don't need to. And now if you define something right in the name my flags, so then you can access should we find enough struct my flags. The semicolon there was not right. So my flags, and then you can access any of them. Let's say for example bit 32 is equals 1, and the way this works under the hood is that the code, the compiler will generate code that will then set or clear exactly 1 bit for you. So in this case create, what do we do? Yeah, here we read the whole flag value into a register, then we use a bit set instruction to set a bit at a given offset, and then we move it back. And of course we could also try my bit setting the nibble here. Nibble can have a value up to 15. Let's try it. As you see, alright, and of course it is somewhat uninitialized, but our nibble 5 here got the right value allocated. And if you would try, for example, something like 16 or so, it would not do it. So we can see also here that what it does is it takes the value and then it ORs it with what we want to assign to it, although at this point it will assume that the thing contains 0. So, well, 15 was not a good test case. Let's go with something that is less than 15. Let's go with 13. Something where we will need a bit clearance. So now what it does is first it clears the nibble, so it makes an end with everything we want to clear, and then here it fills the new value in. So it is quite efficient, and this can be improved even more. So if we first make this to be a union, and then we make the structure inside, we don't need to give the structure a name as we saw earlier, because now since it starts as a union, we can at the top also have a int let's call it flex, which will then contain, like this integer represents all these values here. So we can now my flex clear everything in one go. So we go to flex equals 0, and then with this one you can easily copy it around. You can pass it as an argument to another function. You can basically give the whole thing to whatever you have that has a 32-bit number, and then you can still access what was it, nibble 5. It's in we can access byte 1 is equals I don't know, 35, whatever I want. If you would try to assign a number bigger than what fits inside, the compiler would truncate the number. So if we try to assign 0xff, then we will see that we will not overwrite the other nibbles. So when we take a look at this, we see nibble 5 was probably set, but 6, 7 and all the others have not been affected, and only this byte here is set because we want it to be set. So using this notation, we can very easily dissect and reassemble various data which we can only access on which we want to access on a single bit level. Without this mechanism, we would need to pretty much do the same what the compiler does: clear bits at the right offsets manually, shift things in, shift things out. So it would be much more complicated and significantly less user friendly. So this is a trick worth remembering. By the way, you could use such a trick with the homework that was assigned last time to easier access the individual parts of the number. Instead of using shifts and so on, you could have used such a union. So this is quite a nice trick. And I think since the time is running short, the last thing to show you would be an example of what I mentioned earlier, how to use these unions to create a sort of polymorphic data type. So let's say let's call it my data, and here what we have seen earlier with variables, we saw this enums. So let's create an enum. We don't need to give it a type, but we need to use it. So let's call it data type. So the member is called data type, and types undefined is 0, type 1. Yeah, I'm being particularly creative here. 1, 2, 3 and 4. Usually in reality you would then use some more meaningful names, obviously. My data, at this level we cannot do much. We can just set data type is equals, we need my data as namespace, type 1, and now the union comes into play. Of course we could have maybe some other fields like size, size t, size. So let's say we want to also have size here. You might wonder what's the purpose of giving the structure a field of the size of itself. That's actually quite useful, because if you would have some APIs where you might want to change the version, or not really change the version, extend your structure with additional fields. If your structure would have such a size field, then when your API gets called, you can look on the size, and then you know how many of the fields that you have are actually in the structure. So if you added fields and then you have a newer library, but the application which is calling some function in your library does not support this newer fields, then it would have a definition of your structure which is smaller, so the usize would be then set to a smaller value, and then your library based on the usize could detect that this structure is like not version let's say 2 but only version 1, and then act accordingly by ignoring the unneeded fields. A bit more aggressive approach would of course be to have like a version field, and then if the version is one that you don't know, then just say, okay, I cannot work with that. But then, as you see, obviously then you have to sometimes not work, which is not good. So you don't have like backwards and upwards compatibility. That's pretty much what I am trying to say. But using this method with the size, and then always using a structure which is which only can contain additional fields, but the order of existing fields will never be changed as such. It gives you the ability to be within reason upwards and downwards compatible, because if you get some newer parameter set which you don't know what to do, you can just ignore them. Or if you are returning some structure, then you would just not set the new parameters which are not yet known by the by you, but known by the application that was requesting that. And of course, if you would get like an empty structure to be filled in, where the usize is also one of the fields, then you could of course set it to a smaller value which you know, so that the program which called your library and then try to get some data could then inspect the usize size and see, this is smaller, so I have to ignore some of the parameters because they would not have been filled in. So that's what this is good for, and now we will use our size, our union, or a union. We will give it a short name u. Although, as mentioned earlier, we could, if we don't give an union here a name, then everything that's inside of it would be available on the top level. So in some use cases that makes for nicer code, but here let's stick with giving it always a name, and then inside we just define structs. Which will be representative of our different data types. So let's say data1 int test 1, 2, 3 and 3 and 4. Now obviously it's kind of pointless if they're the same, so let's make them slightly different. This will be an int var a, and then it will have a let's be very basic with the first one, a b c and d. This one may contain a int64 int64 param1 and another int64 param2. This one can contain, let's say, test A and test B and another param. This is kind of boring because they are all the same currently from the total size. So let's just make this slightly smaller, just param, test and param. And this one can contain a whole other structure. X data right here, and now the size of your of our my data is as small const int my data len is equals size of my data. So it is as small as it gets. Well, in this case 40, since well, the smallest, this one is here 24. And this will take some room and some alignment, so I think this will get so without anything this should be probably 24, right? And we get instead of 24 we get 40, so 24 to 40, how much we guys that 1 goes 32, so it's 2, 2, 2, 8. So in total we have 64 bit which we are wasting, I assume. So first of all, this one will be 4 in size, so we are wasting another 4 here because this one is 8. And I guess the rest will be just somewhere here. It sounds like it looks like it's 1 too much. Okay, if we remove all of that, we should have the size of 16, which is... Alright, that's fine, 16, and then 24, this gives us 40, so we don't have any additional padding. That's how it would look in reality. This is 24. Of course, when we would here, for example, add now, let's add a maybe here a third parameter, time. Actually, maybe let's add it here, because this here gets a empty 4, so we have 8. That will not be enough. No, that will be enough. No, that will not be enough. This is still bigger. Yeah, let's just go with 4 parameters. Because now this thing is for 8, 16. This thing is 32. This thing is 16. Oops, 16. This thing is 24. And the whole thing obviously then becomes always what's the biggest, so the biggest is 32, so it will be 32 plus 16, so we should have like 48, right? So as you see now, you can have a structure. You will set the type and something. Then if we set type 1, then you would access u.data1. Var a is equal to 1, 2, 3, 4, 2, 3, 4. I forgot the semicolon. A, B, C, D. And then somewhere further down in your code, things will happen, and at some point this structure gets again to some code that wants to do something with it. So, for example, what you would do is you would have a switch which takes the data type. I don't like the name. Let's call it just E type. Yeah. So switch for your E type, then you have case my data E type 1 doppelpunkt break 2, 3, 4 2, 3, 4. Then of course in this case you would know that you can access those values int test. Oops. Equals this, and in this case you would know, okay, you need to use data 2. Maybe you're interested in param, I don't know, param 1. And so on and so on and so on. So you save on the memory, because all the different variations of your program, of your data, sorry, all the different variations of your data occupy the same memory, but at any given point in time only one of its, let's say, incarnations is valid, and this you would usually determine based on some additional variable that you have attached that allows you to determine the size, sorry, the type, and which of the included data structures are valid. And in principle, after such a union, you could even here also have some additional variables, but of course then you would not be able to change here any of those structs by adding something, because then if you want to have your backwards and forwards compatibility, the offset of this variable would change. So it is of course recommended in such scenarios to have your union as the last member, so that if you decide to add even more thingies, oh, we dropped the 3 even more thingies, then it will not impact any other offset in your structure. Okay, since we are already kind of running out of time, and we didn't make a break, so this time, sorry about that, I will try to remember next time that there should be a break. So I think it's a good point to finish for today. We had a quite exhaustive look on pointers and structures, and if I recall correctly, next week is a holiday, and the day after that, and the week after that is, no, it's not a holiday, it's just Ferien, how to call Ferien in English? Well, break. It's just free from lectures for the next Easter break, yes. So we will see each other in 3 weeks from now. Where's my calendar? That will be the 11th of April, if I'm not mistaken. So you have plenty of time to finish your homework. Yes. Are there any questions? Mm-hmm. You may yeah. If you have a normal C array, there is not. You need to have the size or the address of the last element. I will create a small new project, because in the very modern C, if you are using C++, is that what's called? If you use C++ and STL templates, so create a project, then there is a way how you can, in a specialized case, iterate through things. So we include, for example, vector. So this isn't like reaching far into the future of what we will do in the lecture, but it fits with loops and arrays, so let's quickly talk about it. C++, especially the newer versions, have a standard template library. What templates are and how they work we will learn also much later, but the general idea is that you have this vector type, which you can instantiate, telling it which type you want your array to contain. My vector, and then this thing is an array of which has a variable size, so it can be resized. So you can resize it to, let's say, 10 elements, and then you can use the square bracket operator to access every entry. Well, of course, we need to every entry in it. And here you are not running the risk of accessing invalid memory. If you try accessing 10, so 1 too much, then this will throw an exception, because for every of these accesses it will check whether the address you try to access is actually valid, or whether it is already outside of the bounds of your memory that was allocated when resize was invoked. And there is a new type of loops for int double point vector, and here we could do something with it, and this loop will iterate through every element from the 0th until the 9th, so this will not work, and invoke the body of the loop once for every element. But it's kind of implemented in a convoluted way. It gives you this nice loop, as you probably know. It's similar from how you can iterate through the elements in a array in Python, but the way it's implemented under the hood is a bit more complicated. So the old way of doing it would be to define a iterator. This is an object which points, it kind of is a sort of I don't want to say it's a sort of pointer, because it kind of is not, but it is also pointing to something. So in this case, right, it will be kind of referring to the first or rather, let's say different. It's an object which is complex, has a few things inside, and among those things, it contains a pointer to an element. And you can get like an iterator that belongs to the very first element in the array, and then for how far you go, you are testing whether I is not equals end. And this is kind of so this also would be an iterator, but it would have a special value indicating that it is not longer valid. And if you use the ++ operator on the iterator, this is not a mathematical +1 or anything. It's just a function which you can invoke by using the ++ operator, which would advance this iterator internally by 1. And inside the loop, you can, I don't like autocomplete. Autocomplete is annoying. You can use a overloaded asterisk operator to access whatever this iterator points at. And like this code was available, this type of writing code was available since I don't know, like C98 probably, but in the much newer versions, I think it was introduced with C11. Effectively, if you write a code like this, then the thing will abstract away the first part of the loop. It will kind of implement this for you. So this part is equivalent to this part, but this part is of course much nicer to write. And it's actually something we could do in one of the later lectures. We could write our own safe array container, which can contain objects of an arbitrary type, which ensure that we cannot access an invalid offset, and which would be iterable through this. So this method is not constrained to only STL types. It only requires, in principle, there being a begin and an end function, which return an object on which you can make asterisk, and I think which has an ++, on which you can make a ++, and which has the asterisk operator. And another really nice thing about modern C++ is that if you have a return value of a given type, you don't need to write the type down. You can just write auto, and C++ will for you automatically look up which return value begin in this case would have, and then fill it in. So yeah, that much to that. To summarize it, on the level of modern C++, you can use something similar. On the very basic level of just C, there isn't such a mechanism. You need to do it manually. Okay, any other questions? Yes? Well, the most elegant way would be you would have some main.c or main.cpp where you implement your test, and then you have I mean, this is a very trivial program. You just need one main file, which will then just have some code at the beginning, and further down in your main function you can have some test cases. So once we have did done functions, then you can create a more advanced test suite. But as long as we haven't taken a look into function and function calls, then at the level of what have been presented until now, we are constrained to just have one single main function. Everything then should be inside there. And I guess you can take away that this printf will print whatever you have to the console. We can quickly run it. So you could kind of have an if and then printf success or printf failure. And if you want a new line, you need to use \n. So that is something that you could do. But you could also just set variables, and that then at the end just write in a comment, inspect variables such and such, and they all should be true if every test was successful. So yeah, that's that. Okay, any more questions? Okay, if there are no more questions, then I guess it's a good point to stop. If you've come up with any questions, any urgent questions over the holidays, the break over this, then you can write me an email at any point in time. I will try to answer it as good as I can, as quickly as I can. And yeah, that's that. So we will see each other next time, and have a nice Easter holidays. Bye bye.